In this question, we've been given a starting value of 125,000 and we're told it's going to decrease by 2% per year for 3 years, and we've got to try and figure out the value after 3 years. So this is a classic depreciation question. There's no real magic to this question type, you just got to know the process. So if our starting value represents 100%, we're taking off 2% because it's decreasing by 2%. So that leaves us with 98%. 98% as a decimal is 0.98, and that's the number that we use when we're working with percentages, the decimal version. So all we're going to do in this question is take our starting value and multiply it by 0.98, and that basically does two things for you. It calculates 2% and takes it off. You could work out 2% of this value and take it off, but that's a two-step process. Just by multiplying it by this number, that is taking 2% off all in one go. The only issue is this would be 2% taken off for 1 year. We need to do it over 3 years, so you could complete this calculation 3 times, but that's just going to be time consuming. So we've got a way of speeding it up, making it more efficient, and it's just to put the time period as a power here on the decimal that represents the percentage change. So we're basically just taking your starting value, multiplying it by the percentage change to the power of the number of years or whatever the time period may be. If this had been increasing by 2%, it would be 102%, which would be 1.02. So it's just a case now of putting this in the calculator. So just make sure that you're careful with the sort of calculation part. It's easy to make a kind of little numerical mistake. And also, it's just worth keeping in mind that you should check that your answer actually makes sense. You know, it's very easy to make calculator errors, and if you make an error, the answer is going to be thrown off quite significantly, so you've got to make sure the answer actually makes sense. So 125,000 times 0.98 to the power of 3, so that comes out to be 117,649. And sometimes these questions will ask for it to be rounded. In this question, they're not asking for it to be rounded, so that is our final answer. So 117,649. In this question, we've been given a diagram of a sector, which I've very badly tried to replicate here, and we're asked to find the length of the major arc. So a major arc is an arc which is more than 180 degrees, so it takes up more than half of the circle. And you can see that the arc here from A to B, which is what we're trying to find, is clearly more than 180 degrees, so that's why it's a major arc. We're also told that the angle in here at the center point, so this angle around here, is 320 degrees. And this is just a straight up arc length question really, so we just need to remember the arc length formula. So arc length, this formula is not given on the formula sheet, so you do need to commit it to memory. So it's just the angle at the center there divided by 360. So that gives us like the ratio, the part of the overall circle that we want. So angle over 360 times, and then for arc length it's times pi d. For sector area it's times pi r squared. So let's just think, do we have everything we need? Well, we've got the 320, which is the angle, so it's going to be 320 divided by 360. Pi is obviously just pi. Diameter, we've got radius, 7.4, so we need to double that to get our diameter. So it's going to be 7.4 times 2, which is 14.8 to get the diameter. And because this is a calculator question, there's nothing else really to do. This is a very straight up question. We just need to put these numbers in the calculator now. So just doing that very carefully. Easy to make computation errors. And it's also good just to have, I think, a bit of a guesstimate as to how long that could be. So we know that's 7.4, so try and figure out how many 7.4s would go into that arc. And that'll give you a bit of a guesstimate for what the answer might roughly come out to be. It's not going to be like super accurate, but it'll be roughly in the right ballpark. Okay, so this comes out to be 41.33. And just checking the question or checking my diagram, it's in centimeters. So this is a length, remember, so that would just be centimeters. So a very straight up example of an arc length question. Really the key with these questions, arc length or sector area, mostly is remembering the formula. It's not on the formula sheet. A lot of students forget the formula, but once you remember it, just be careful with the numeracy. Careful also with the fact that they'll often give you radius when the formula demands diameter, or in a sector area question they'll give you diameter but the formula demands radius, so converting one to the other. So that's the answer for that one, 41.33 centimeters. In this question we've been given this vector r written in component form and we're asked to find the magnitude. So there's no real magic to this question, you just need to know how to find the magnitude of a vector. So magnitude is represented using the bars, so we put the bars on the side of the vector. Remember that lowercase vector letters are written with a line underneath to represent the vector. If this was in a textbook or in an exam paper, it would be written in bold, but we need to put the little lines in. And basically the formula for the magnitude of a vector is just the square root of each of the components squared and added together. Now that should look familiar from Pythagoras. It is just Pythagoras with an extra added dimension. So it's effectively like finding the long side of a right angle triangle, but with an extra dimension. So we're just putting in the component squared. Be careful with the negatives. Remember you need to put that in a bracket, and they'll almost always put at least one negative component in these questions just to try to sort of catch you out, I suppose. So that's effectively our formula. This formula is not on the formula sheet, so you do need to remember it. So just go ahead and start putting these numbers into your calculator. You can put this all in one go, but if you're going to do that, be very careful. I'm just going to break it down. So this would be 576 for the 24 squared, 12 squared or minus 12 squared is 144, and 8 squared is 64. So just go ahead and add these together. Okay, so it's 784. So it's going to be the square root of 784. Generally, these come out to be a whole number for the magnitude. They don't have to be, but the questions are normally designed so that when you get to this point, when you square root, you will get a whole number. So that's kind of a good way of sort of checking it, because although it doesn't have to be a whole number, it almost certainly will be. So we're hoping that this will square root to a whole number, which it does, fortunately. So my numeracy must be correct, and this comes out to be 28. So the magnitude of the vector is the size of the vector, the length of the vector, if it was written drawn as a little line segment like this, but we don't assign units to vector magnitude, so we're just going to leave it at 28. So 28 is the magnitude of vector r. In this question, we've been asked to solve the inequation. Inequations work very similarly to equations, perhaps with potentially a couple of little twists. Sometimes they work identically to equations, so just kind of thinking in the same way as an equation, which is really just about gathering all the x terms on one side and all the number terms on the other. Doesn't matter which side you do that, but there are some quirks there which we'll chat about later. Anyway, in the first instance, we need to get rid of the bracket. That would be true for an equation or an inequation, same thing. Brackets sort of get in the way. So we're going to get rid of the bracket by multiplying the 6 into the bracket. So 6 times x gives us 6x. 6 times negative 1 gives us negative 6. And that's enough for your first line, just to kind of get going. You now need to start gathering the terms together. You might just want to start by combining these. So it's always good to simplify equations fully step by step. That's really what we're doing with every step, every line of work, and we're just simplifying. Negative 6 minus 12, that's not a double negative, so that just goes to negative 18. That's just the number negative 6, take away another 12, so it's going more negative. And this is where you've kind of got to make a decision as to which side you want to gather your numbers and your letters on. We've already got the numbers over here. There is only one number term now, so it makes sense to put the letters, the x's on the left-hand side. So moving the 6x over, it becomes a negative 6x, so you're going to have 3x minus 6x, which would give you minus 3x. Okay, like that, and that is less than minus 18. This is the part you've got to be careful with. So we're now dividing by negative 3. So on the right hand side it's going to be minus 18 divided by minus 3. But remember that with these inequations, differently to an equation, we've got to do something when we're dividing by a negative. And the thing we've got to do is to spin the sign around the other way. So just got to remember that little rule, and it's only if you're dividing by a negative. It doesn't matter about this number being a negative. It can be positive or negative. It's the one you're dividing by. And if this was a positive and that was a negative, you wouldn't need to spin the sign around. It's only if that one's a negative. And then just carrying on, so we've got x is greater than, the negatives here cancel each other, and 18 divided by 3 is 6. So the final answer is x greater than 6. So it should be a fairly straightforward question. You can avoid this scenario because at this stage here, I could have chosen to take an alternative route. I could have taken the 18, the minus 18, and put it on the left-hand side, which would then become a plus 18. And I could have taken my 3x and moved it to that side, which would then be 6x minus 3x to give me a 3x over there. And if I then solve it from here, I would have an x on that side. 18 divided by 3 is 6, like this. And I've got x is greater than 6. And you could even spin that around to go like that. And notice it comes out to be the same answer. So some students prefer to do this to keep everything positive. Some students are happy with the negatives, but if you do it this way, you've just got to remember to switch the sign around. And that's really the only quirk that ever comes up in equations. In this question, we've been given these numbers and we're told that they represent the number of customers who've attended a farmer's market on a particular day, on a Saturday I think it was. And in the first part of the question, we're asked to make the mean and then the standard deviation. So we need to make the mean as part of making the standard deviation. Remember, the mean is just a measure of average. It's the one that we commonly think of as average, where we just add up all the numbers and divide by how many numbers we've got. So let's just start with that part. So it can be a little bit time consuming these. You've got to show your working. So the working is that we're just going to add these all together and divide by however many numbers we've got, which is 1, 2, 3, 4, 5, 6. And then it's literally just a case of putting that into the calculator. So just got to be careful with the calculation. Remember, the number should come out to be somewhere in the middle of these numbers because it is a measure of the average. So just put the numbers in carefully. 125 plus 131 plus 130 plus 124. Divide that by 6. Okay, so that's come out to be 126. And remember, we use the x bar to represent the mean. So the mean in this case is 126. So we've now got to use that mean as part of the process of manually getting the standard deviation, which is a bit annoying because calculators can do it for you, but they want you to do this manually. So that there is our mean. Let's move on to the standard deviation. So we're going to do this by making a little table. And the table has a few different rows and columns. So in the first sort of column, we've just got the numbers. So let me just kind of set this up actually, first of all, as a table. So the first column is just going to be the x numbers. The second column is x minus x bar. So that's going to be the current number from the x column minus the mean, which is 126. And then in the final column, we're just doing x minus x bar, so the number we've generated here, and then all of that squared. And we're just squaring really to compensate for the fact that some of these will come out to be negatives. We want to turn them all positive, and that's really all that we do with the squaring part. So we're just going to go ahead and put in the numbers. You've just got to be patient with these questions. There's quite a lot of working to do, not a lot of marks usually on offer, so they're kind of frustrating in a way. But it should be easy enough marks. You've just got to follow the process. So just quickly putting in all the numbers like this. And then we're doing x minus x bar. So this number minus 126. So in the first case, that would be negative 6. Sorry, a lot of these you can do manually if you're just careful. This would be 126 minus 126, which is 0. 125 minus 126 is negative 1. This would come out to be positive 5. 130 minus 126 is positive 4. And then 124 minus 126 is negative 2. You just got to go through this carefully. You can usually do them without the calculator. Because these are fairly low numbers, you can probably do the next part non-calc as well. That's not always the case. Sometimes with these, the numbers will be higher. The whole point of squaring it, like I said, is to turn these positive. So you don't even need to think about the negative when you square them. Minus 6 squared and 6 squared are both 36. Next one would be 0, then 1, 25, and then 16, and then 4. Okay, so what we do now, remember the table is just to help control the calculation, to help you keep track of the calculation. And then we're just basically going to add these all together. And so this is the kind of sigma part of the formula, which we'll chat about in a moment. So some people like to notate this as the sigma like this equals or something like that. But basically just totaling these up. So we've got 36 plus 1 plus 25 plus 16 plus 4, and that comes out to be 82 in this case. This is when you might want to turn to the formula sheet. The formula is on the formula sheet if you can't remember it, and it just says that the standard deviation So standard deviation is equal to, so there's a big, well, let me just kind of do it this way. So we've got the sigma of x minus x bar squared, which is the part that we've already done. So that is just going to be a number, and that number is this number because we've taken the x minus x bar squared, and with sigma means add things up. It's a Greek letter that means add things up. So we've added up all the x minus x bar squares and we've gotten that number. We'll be plugging that in a second. And then the formula asks for us to then divide this by n minus 1, where n is the number of numbers. We've got 6 numbers, and then basically to put a big square root around all of that. So we can go ahead and just plug these numbers in. So it's going to be the square root of our top line is 82 divided by, we've got 6 numbers minus 1 is 5. And we've just got to go ahead and calculate that very carefully. So 82 divided by 5, and then we are square rooting that, so it comes out to be 4.05. So I think I'll just call that 4 actually, that should be close enough. So standard deviation has come out to be 4. Standard deviations on their own don't mean anything. This number could mean different things in different stories. It really just works in comparison to another number, which is what the part B's of these questions are normally about. So pretty time consuming, just got to go through that carefully and you should be fine with that question type. In part B of the question, which I've got on a screen over here, they're asking us to make 2 valid comments, comparing basically the mean that we've got here in our standard deviation to the mean and the standard deviation that they've provided for another day, for the Sunday. So a good way to maybe do this is just to have like the 2 side by side. So we've sort of got the new values and we've got the old values. So the new values that they're giving us are 117 and 6.2. So 117 represents their mean, and our mean is 126. And the 6.2 is their standard deviation. Our standard deviation was 4. So what we're doing in these comparison questions, we want to write a statement by comparing these 2 things. So here we've got the mean, this is like our x bar, and here we've got the standard deviation, and we're just going to go ahead and compare them. So first of all, what has happened here to the mean? Well, it started off in our scenario as being 126. It's gone down to 117 in the new set of data. That means it's decreased. The mean is a measure of average, so you've got to get the keyword average in here. So you can say something like, on average, the number, and it's just about fitting this word in with the question. So on average, a number of customers was lower on Sunday. So I think in this question, remember the new was a Sunday and this was a Saturday. So on average, there are fewer customers at each of the stalls on a Sunday. So that's what we can say there. We can't say there were fewer customers at each stall. We don't know that. We just know that on average, there were fewer because this is a measure of average. Standard deviation measures consistency. So we can say that the old standard deviation was 4 and it's gone up to 6.2, but higher standard deviation means less consistent. So the comment we're going to make about the standard deviation is not just the standard deviation is higher, that's obvious, but something like the number of customers attending the stalls on Sunday was less consistent. And these comparison questions are all about getting the keywords. If you're comparing standard deviations, you're comparing data that tells you about consistency. If you're comparing average or mean, then you're talking about the average. You've got to get either these keywords in there or words which very closely mean something close to those keywords, or else you will not get the marks. It's not enough to just say the mean has been reduced. has lowered and the standard deviation has increased, that's obvious. That's not enough. They want you to go a little bit further than that. So standard deviation questions, not particularly difficult, but very time consuming. You've got to manage your time carefully on those questions or else it will start to affect your time for other questions. In this question, we've been given this function, f of x equals 5 plus 4x. And remember, a function is really just a formula, a rule. It's a way of turning an x value into some other value according to the formula. Sometimes in these questions, they just give you a number to put in here, like 3 or something, and you do f of 3. You just work this out by replacing the x there by 3. This one's more difficult. It's almost like we're working backwards. We're being given some a value, and when you put that a value into the function, you get out 73. So just to quickly go the other way, say the question was easier. Say they asked you to work out, say, f of 2. Well, that would mean just going 5 plus 4 times 2, so replacing the x with 2. So 5 plus 4 times 2. This is not what they're asking in the question. I'm just showing this for demonstration. So this would be 5 plus 8. 5 plus 8 is 13. So in this example here, we've put 2 into the function and we got 13 out of the function. And that's often how these questions are. This one's more difficult. They're saying if you put some number into the function, you get 73 out. So it's like they've given us this value and they're asking us to work out this value. And they are quite tricky, these questions, but the way you've got to think about them is, well, if I did put a into the function in the same way that I put 2 into the function, what would that mean? Well, it would just mean replacing the x with a, because that's all we do in a function. If we change it to the x to a 2, we put a 2 there. If we change the x to an a, we're just going to put an a there. So it becomes 5 plus 4 times a. So this here, 5 plus 4a, is f of a, and this here, 73, is also f of a. But they're both f of a. If they both represent the same thing, then they are the same thing. In other words, they're equal. So we can just take these two things and set them equal to each other. So we can just say that 5 plus 4a is equal to 73. So we've basically constructed a little equation, and from that equation we can solve to get the a value. Just a normal linear equation at this point, so we're just gathering the numbers on one side and the letters on the other. So 73 minus 5 is 68. And then we're just going to go ahead and divide that by 4. Okay, and that will divide by 4. This is a calculator question. Anyway, you could just put that in the calculator, but that comes out to be, I think, 17. Just quickly check that. Yeah, 17. So that's telling us that if you put 17 into that function, f of 17, you would get 73 out. But this is an example of a function question where you're working backwards. Sometimes these questions ask you to do this as a part A and then this as a part B. This one is just going straight in with a more difficult version, so it is a tricky little question. But anyway, that is the answer for that one, A equals 17. In this question, we've been asked to work out the volume of a sphere, which has got a diameter of 6.4 centimeters. Nothing else really given in the question. I mean, could not be an easier example of a volume question. The volume formula for a sphere is on the formula sheet. I'm just going to do the work in here. So in fact, no, I'm going to do the work in here. So the volume formula is 4/3 pi r cubed. And that's pretty much it. And it's also a calculator question, so we can just put all the information in the calculator. Just be careful by the fact that the formula needs for radius, but we've got diameter. Radius is half of the diameter, so our radius, or R value, is going to be half of 6.4, which is 3.2. And then we're just going to plug that into the formula. So this is just, it's good to write this down. So it's going to be 4/3 times pi times 3.2 cubed. Okay, so just writing that down, populating the formula before you start doing any calculation, you'll probably already get a mark for this. And then it's just a case of calculating that carefully. It's not always easy to know whether your answer makes sense in a volume question. In other geometry type questions, you can see by the diagram it makes sense. You've just got to really calculate these very carefully and trust that the answer does actually make sense. Okay, so this one has come out to be 137. I'll use a couple of decimal places here, so 0.26. Because it's a volume, that would be centimeters cubed in this case. But in the question, they're asking for it to be written to two significant figures, so it's not decimal places. significant figures. So significant figures, you're counting in from the left. So hundreds, tens, units. 1, 2, they're asking us basically to go to the tens column, so to the nearest 10. So 137 to the nearest 10 is 140. So it's going to be 140 centimeters cubed, and that's two significant figures. And that's basically it for that one. Very, very straight up example of just picking the formula off the formula sheet and putting the numbers in carefully. In this question, we're being asked to solve this trigonometric equation, and all trigonometric equations come with a corresponding range of values, and the range of values just tells us where the solutions are allowed to lie. So in National 5, it's always pretty much 0 to 360, which means that we should be getting two solutions for our equation. So this doesn't massively play a part in the question. It can if this starts to change, but because the standard technique kind of accommodates this scenario anyway, you don't massively need to worry about that. You don't need to physically do anything with this. Okay, so turning to the equation, the first thing is to get it rearranged to the trig function. So in other words, getting the sine x on its own on one side of the equation. So just kind of basic algebra here. So we're just going to start by moving the 2 to the other side. That becomes a minus 2. So 3 minus 2 is 1. Dividing both sides then by 7 to get 1 over 7. And really at this point, this is where you need the CAST diagram, the dreaded CAST diagram that everyone hates. Remember, the CAST diagram, it doesn't generate any marks. It's just a way of predicting where the solutions are going to be. And that helps you particularly for finding the second solution, but also validating the first solution. So you just need to know how to draw the CAST diagram. So CAST, remember this is C for cosine. A means all, it actually means all positive. And we'll maybe explain that in a second, then sine, then tan. And also the label, so 0 degrees, 90 degrees, 180. And you might find that by exam time you don't need to draw the CAST diagram anymore. You might just know these off the top of your head. That's fine. You wouldn't lose any marks for that. So how does it work? Well, we've got sine and we've got a positive value. It doesn't matter what the value is, just the fact that it's positive. Sine positive, you'll be checking the A quadrant and the sine quadrant. If it was sine negative, you'd be checking the other two, and that's just the way it works. So what does that tell us? Well, it tells us when we solve our equation, we should have a solution between 0 and 90 degrees, and we should have a solution between 90 and 180 degrees. And all it's really doing, the CAST diagram, is giving you another way of thinking about this information on the graph of the function. So just to quickly show you this, if you draw a sine graph, because we're dealing here with a sine function, and remember the highest point, the maximum value in a sine graph is 1, the lowest point is at minus 1, and this point in the middle here is at 180 degrees, and then the end point is at 360. If we mark on 1 over 7, 1 over 7 is a very small number, so if you mark that on going up the way, that would be, I don't know, like here maybe, somewhere there, so that's our value 1 over 7. And if you just draw a horizontal line through the graph, where it hits the graph, that's going to be your two solutions. So a solution there and then a solution there. So you can see, remember this point here by the way is at 90. So you can see that there's a solution between 0 and 90, and there's another one between 90 and 180, which is just what the CAST diagram is predicting. And in fact, in some ways this is more accurate, because you can see that this one's pretty close to 0. It's going to be a small number, and this one's pretty close to 180. CAST diagram doesn't really tell you that, it just tells you where in the quadrants it's going to be. But these are effectively telling you the same thing. So now we're just going to turn to the calculator, and we're going to go ahead and do sine inverse. So sine inverse of 1 over 7. Okay, and that comes out to be, as predicted, quite a small number. So it's come out to be 8.2 degrees. So that is basically the solution in here. That's the solution here on the graph. So that's 8.2 degrees. Second one we're going to get by doing 180 minus. So we're going to do 180 minus 8.2. So 180 minus 8.2. We could probably have done that without the calculator. So that comes out to be 171.8 degrees. And again, that's in the right quadrant and also on the right place according to the graph. So you don't need both of these. This is a standard method. But in a way, like I say, this is more accurate, but they're kind of saying the same thing. Just make sure you assign your final answers to X for these questions. So x equals 8.2 degrees, and x equals 171.8 degrees. You won't get the marks if you don't assign it to x, because it is x we're trying to solve the equation for. So those are the two solutions for this trigonometric equation. We've been given this triangle and we're asked to find the length of C to D. So this side here of the triangle is clearly a non-right angle triangle, so therefore it's not a Pythagoras question. It can only be therefore sine or cosine rule. So always got to go through that thought process. Is it going to be Pythagoras or is it going to be sine or cosine? At this point we don't know whether it'll be sine or cosine. That's what you've always got to decide. That's what makes these questions quite challenging. But one thing we can see at the moment, our triangle, which is here, has got one side length and it's got one angle. That's not going to be enough to find the other side length using either the sine or the cosine rule. So there must be more information in the question, because there's no way that we can use either rule with just those two pieces of information. But we've got the 75 here. Notice the 75 degrees is not inside the triangle. If it's not inside the triangle, it's not an angle we can use in the sine or the cosine rule. Sine and cosine rule angles only refer to the internal angles. But because this is a straight line from A through B down to C, we can just use basic geometry to say, well, if that's 75, this would have to be 105 because the angles in a straight line add up to 180. So just using a bit of basic geometry. It might even be that we need to then work out this angle here, and you could do that by adding these together and taking them away from 180. I'm not sure if we'll need that one, so we'll just leave that one for the time being. So now we can think about it. Okay, we've got two angles. One of them's opposite the side we're trying to find, and these are also opposite each other. So that's a good candidate for using the sine rule. If we wanted to use the cosine rule, then we would need more information, and in particular we would need another side length. If you want to use the cosine rule to find a side length, you need the other two side lengths, but there's no way we can make the other side length. So we're good to go, I think, here with the sine rule. So the side we're trying to find, this one here, is little b according to the diagram. This is little c, and then this over here where the 20 is d. So we're using b, c and d. A little bit awkward because the a is not really involved here, and the formulas, remember, are written on the formula sheet a, b and c. So we're actually doing a bcd triangle. So we're going to make it as b. So our sine rule is going to be made b over sine b equals c over sine c equals d over sine d. So just updating the normal formula from the formula sheet, and then thinking, right, what do we need? Well, we need the little b. That's what we're trying to find. We've got angle b, so we're definitely keeping this one. We don't have side c or angle c, so that's the one we're going to be discarding. And we do have the d information, so we've got everything we need, and we can start populating it now. So b is staying as b because that's what we're trying to find, and we're dividing that by the sine of angle b, which is 105. So sine 105 equals d, which is 20. Diagrams are really important to remember in these questions. Get them fully drawn out, fully labelled, and then the sine of angle d, which is 37. And just by getting to this point, you've already generated quite a lot of marks, and now we're just trying to finish the question off. We're trying to solve to get the b. To do that, we need to get the b on its own, which means we need to move the sine 105 to the other side, and we're doing that by cross multiplying. So it's going to go from the denominator here to the numerator here. So b is going to end up equaling 20 sine 105, or 20 times sine 105 divided by sine 37. And we can just put this in the calculator, but it's good to predict with sine or cosine rule or any geometry question the answer based on the diagram, just so that you can check whether, I mean, just by looking at that, I've got no idea what that's going to come out to be, but I can kind of check what I think it should come out to be by checking my diagram. So this side here is 20. If you imagine sort of spinning that around to there, 20 would be to there. So it's clearly longer than 20, maybe not quite double 20, but somewhere in that ballpark. So we should be expecting an answer in that ballpark when we come to calculate it. So just putting these carefully into your calculator. Okay, cool. So that came out to be 32.1, and the unit is here is centimeters. So 32 is approximately like what I kind of guesstimated. to be a little bit bigger than 20, but not quite double 20. So it's always good to make those guesstimations. So one thing to look out for in sine and cosine rule is when you've got an angle given that's outside the triangle, it's not going to be there to throw you off. It's going to be there for some purpose, but it'll be there to help you create other angles which are inside the triangle. You cannot use angles outside, only angles inside. Also, you can never generate side lengths by doing sort of geometry like we can with angles. So if you don't have enough side lengths to use the cosine rule, then by default it would have to then be the sine rule. Check the cosine rule first. It's always got stricter requirements. You'll be able to tell quite quickly if it's going to work. If it doesn't work, then it has to be sine rule. There are only the two rules, so it has to be one or the other. In this question, we're asked to express the vector BC in terms of u and w. So that really just means, how do we start at point B and get to point C, working our way around the shape, around the diagram, using the vectors u and w and not going in any other direction. So to get from point B to C, there's only two options because it's quite a simple diagram. We can either go from here to here, or we can go all the way around the shape. We've got to take the option which will allow us to use the vectors u and w. Now, the vector u goes like this, vector w goes like this. Any variation on those, like any different angles, are not going to be the vectors u and w. So the vector u is here, but the vector u can also be pulled down here or here. As long as it's at the same angle and it has the same length, the same magnitude, it doesn't matter where the vector is, it's still the same vector. But these vectors u and w and this line here are at different orientations. So this line here is not an option. We can't go from point B to point C that way. So that means the only option is to go around the shape this way. So let's just think about that in terms of writing the vector. So we're trying to write the vector or express the vector BC. We're going to do that by, if you imagine this being a journey and these were, I don't know, like points on your journey, your first part of your journey would be from B to A, then from A to E, and then from E to D, and then finally from D to C. So just maybe write that. So we're going to split this journey as the vector B to A. Okay, so going from B to A and then A to E. So then add into that A to E, and then add into that, so E to D, just breaking the journey down, E to D, and then finally add in the last piece, which is D to C. So notice that when you do that, this is called a vector pathway. You should, if you're trying to make B to C, you should start with B here and end with C here. And also the internal points have to connect. So if you're jumping from one vector to the next, these have to be the same letter. If you don't have that, then something's gone wrong. So that is already basically the answer, but it's just not expressed using u and w. So we need to now start using the vectors u and w. So this is endpoint notation, uppercase letters, but we want to write the vectors using lowercase letters. Remember, when they're written in lowercase, we put a little line under them. So this vector from A to B, the arrow going from A to B, remember the arrows are really important, the arrow goes this way, so A to B is a vector u, we want to go the other way, B to A, so we're going against the arrow, so that'll be negative u. So that vector B to A is just negative of the vector u because it goes against the arrow. And then the same here, we're going from A to E, but that's going against the arrow of the vector w, so that's going to be minus the vector w, like that. And then we just need to keep piecing it together. And the next two are a little bit more demanding because the vector E to D, this one here, it doesn't have a U or a W on it, but we're told in the question that E to D is 2 times A to B. So A to B is a vector U, so this is going to be vector U and another vector U, so 2 times the vector U. So we're just told that that is 2 times the vector U basically. And then D to C, well, D to C is 2 times E to A, so that means that this length here is 1/2 of this length here. And the arrow, if we're going along this way and along this way, then the arrow is going in the correct same direction as the vector W. So our vector D to C is just 1/2 of the vector W. So it's just plus 1/2 of the vector W. So that's how you go about these vector pathway questions. Start by writing it in uppercase, endpoint notation, and then putting it in terms of the letters that we need. And the question asks us to fully simplify. This basically works like algebraic terms. We're just gathering together the like terms. So we've got 2u here minus u. So 2 minus 1 is 1. So it's going to be 1u or just u. And then we've got minus w. Well, that's minus 1w plus 1/2 w. So it's going to be minus 1/2 w. And that's the final answer for that one. And you can sort of check that because it should be that if we go from point B to point C, we can do that using 1u minus 1/2 w. This is a vector u, so 1u from point B would be like that. So it's going to take us somewhere to here, and then minus 1/2 w, well, that would maybe be a little bit longer, maybe to here, and then minus 1/2 w, that would be going minus this way, like to there. So that does seem to be right. So using the u and the w, we can sort of check that that answer makes sense. So that's the final answer for that one. In this question, we've been given the volume of the planet Venus, and we're told that it's 9.3 times 10 to the power of 11, written in standard form or scientific notation, kilometers cubed, and we're told that that's 85% of the volume of the Earth, and we're trying to work out the volume of the Earth. So this is a sort of classic reverse percentage question, but it's also got the added complication of using these standard form numbers. So this number represents 85% of the volume of the Earth. So a good way to set this up is just to say, well, 85% is that number. So you can set those sort of equal to each other like this. And we ultimately want to get to 100%, which is going to be the volume of the Earth. To do that and to help us calculate that, we're going to go down to 1%. And then we're going to go up to 100%. So you don't need necessarily that intermediate step, but it's a good way to help control the calculation, and you could just skip over it. But I'm just going to break it down in this way. This is the sort of standard way to go about this question. So very much a calculator question because we're dealing with these big numbers. Calculators can handle this form, you know, standard form, scientific notation. I'm using a phone calculator. It's not quite as convenient, but just whatever device you're using, just put the number in carefully. So I'm just going to go ahead and work this number out first of all, or just get this number into my calculator. And then I'm going to go ahead and divide the number by 85 because we're dividing from 85 to get down to 1%. So that number divided by 85 comes out to be, oh, there's a big number. I'll just quickly write it out. So it's not written in scientific notation, just this ginormous number basically. Okay, something like that. And then we're going to multiply this by 100 to get it up to 100%. So just times that number by 100. And that comes out to be like this. Wow, so it's just a huge number. And then we want to write this number. I mean, this is the final answer, but we want to write this number in scientific notation because the question is in scientific notation. So we need to convert this into like this standard form. So the way that we do that is we always use a number like something point something. So because this one's come out with a 0 here, it's slightly awkward. So this would be written as 1.09. Okay, so we don't just leave it at 1. We need to go to at least like 1 or 2 decimal places, so 1.09, and then we can stop there. And then we need to think how, like your calculator might do this for you, but if not, you need to think, right, the decimal place would be here in this number, but we want to move it back to here. So how many places does it move back to get to that point? So it would be, or you could count it forward, so it's like from here, which would be there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it becomes times 10 to the power of 12. And that is the final answer. And that is in kilometers cubed. So a bit of two techniques there, reverse percentages and also standard form. The calculators will handle standard form for you, and they'll sometimes just present the answer in standard form. It just depends how this number comes out. If they don't, you should definitely be prepared to convert a big number or a really small number. The small numbers would have leading zeros. Convert either of those into standard form, and you'll just do that by putting it in this format, 1 point something or whatever the number is, something point some decimal number times 10 to whatever power you need. So that is the final answer for that one. In this question, we've been given this diagram and we're asked to calculate this length here, which they're calling the width. The challenge with this type of question is recognizing what technique we need to use. It looks like sort of a geometry question, maybe properties of shape, something like that. It's actually a Pythagoras question, and Pythagoras questions are recognizable because they're always a circle with a chord line. Okay, the circle has been kind of chopped off here, but if you see a circle with a chord line presented in various different ways, that's going to be Pythagoras for sure. And these come up like every year. So if you see this circle with a chord line, if you have a chord line here, or maybe at the side here, something like that looks a little bit like that, it's going to be Pythagoras. And it's going to be Pythagoras because the way that these questions tend to roll, if you've got, say, the center point here, if there's a geometry property that says if you draw a radius line there, it'll make a right angle with the chord line. So you're basically constructing a little right angle triangle, and that's what makes it Pythagoras, just because of that geometry property. So that's the challenge, first of all, with these, recognizing what type of question. So basically, if you imagine that the circle did continue here, this is not a great circle, by the way. I've drawn more like an oval or an ellipse or something. So if you did carry on the circle, and we drew what would be a radius line, that would go all the way to the edge of the circle, and that would carry on and hit the circle, but it hits that chord line at a right angle. So that is the key to unlocking these questions. And now we can construct a right angle triangle there. Okay, so that's always how you'll start these. Question then is, how do we find what we're actually looking for, the width? Well, the width is the length from here all the way across past the center point to there, but we're going to break that calculation down because from here, the edge of the circle to the center, well, by definition, the edge to the center is the radius, and we're told in the question that the radius is 13, so we already know that that part there is 13 centimeters. That means we've really just got to find this length here, and then we can add that to the 13. But this point here is the center, and that is the edge where I've constructed my triangle, so that is by definition also the radius, so that's also 13 centimeters there. Then we're told that our chord line is 20. Half of 20, which is this midpoint here, is 10, obviously. So that tells us that this side here, let me just write it like this, is 10 centimeters. So basically we've constructed a right angle triangle. We've used some of the information in the question to find the side lengths, and we just need to now find the missing side length. So I'm just going to sort of pull that triangle out to make it a little bit more obvious. So we've got two side lengths, and we're trying to find the other side length. We know it's a right angle triangle. So this here is 13, this side is 10, and we're trying to find this one. This one's one of the short sides, so it depends with Pythagoras very much if you're trying to find a short or a long side. So it depends how you want to set this up. So the classic sort of Pythagoras setup is a squared plus b squared equals c squared. But the more important thing, rather than the actual letters, is that it's the two short sides that square and add together to make the long side. So let's say that we're going to call this side C and this one A, so that it's B we're trying to find. Then that would mean that our A would be 10 squared, so we're calling this A and this C and this B. B is just going to stay as B because that's what we're trying to find. C is 13, so it's going to be 13 squared. And that's how we go about constructing the Pythagoras equation. Now we just need to solve it for B squared and then for B. So we can just take the 10 squared to the other side of the equation, which makes it a negative 10 squared. And then just starting to calculate the numbers. So 13 squared is 169. You can do that on the calculator if you wish. 10 squared is 100. 169 minus 100 is 689. That's still, remember, b squared at that point. So b is going to be the square root of 69. And just go ahead and put that into the calculator. Keeping an eye on the geometry to make sure that the answer actually comes out to make a bit of sense. So that comes out to be 8.3 to one decimal place. So 8.3 centimeters. Now if you think about the geometry, this is one of the short sides, so it should be shorter than the long side, 13. It looks to be a fairly similar length, maybe slightly shorter to this side, so the 8.3 fits in really well. So we figured out then by Pythagoras that this side is 8.3 centimeters. So that means that the width is going to be 13 plus 8.3. So that is what, 21, is that right? 21.3 centimeters. So the actual mechanics of the Pythagoras is not that difficult, but recognizing these questions is challenging. Circle, chord line, it's not geometry, it's a Pythagoras question every time. In this question, we've been given this diagram which shows the positions of a yacht and a ferry and a trawler, and we're asked to find the bearing of the yacht from the trawler. So the first thing is to understand, what does that actually mean? Well, a bearing is starting at a certain point, facing north and spinning around clockwise until you then point in the direction of the thing that you're interested in. So for example, if you're at this point here, putting on a little north line, like this. So bearings questions always have north lines, and let's say there's something over here that we're interested in. The bearing from this point to that point, so let's say this was point A and this is point B. So the bearing from A to B, or the bearing of B from A, depends which way you want to say that, is starting looking north and spinning around until you're facing point B. In other words, the angle there. So let's say that angle was, what does that look like? Maybe 120 degrees or something. So the bearing of B from A would be 120 degrees. And that's the kind of thinking that we need, first of all, in this question. So we're standing, or imagining standing at point T, and we want the bearing from T to Y, or the bearing of Y from T. So they've said in the question, calculate the bearing of the yacht from the trawler. So the bearing of the yacht from the trawler. So that means that we need the angle from this north line all the way around here, past this line to that line. That's what our angle that we're interested in is, just like the one over here. So we're told that the angle from here all the way around to this line is 240 degrees. So to get our answer, we really just need to figure out the little bit left over, which is basically this angle here, which I'm just going to shade in. So the angle inside the triangle. So we've transferred the problem from, first of all, understanding the problem, what are we being asked, like the definition of a bearing, to then breaking it down to say, well, we don't need to calculate the whole angle, we've already got part of it, we just need to calculate the bit inside the triangle. So we're changing the nature of what we're actually being asked here. Now we're saying to ourselves, okay, well, it's a non-right angle triangle, we've been given all three side lengths, what rules have I got potentially to use to get that angle? Well, there's only two rules for non-right angle triangles in the Nat 5 course, sine rule and the cosine rule. That's all we've got to work with. So you would need to ask yourself which rule fits in here. So we've only got side lengths, we don't have any other angle, so that's going to be the cosine rule. So the cosine rule to find an angle written on the formula sheet says that cosine of A, formulas are written with A, B and C, is equal to A squared plus B squared. Sorry, no, it's not. Let me just change that. B squared plus C squared, I should have written there. So you can check this obviously on the formula sheet. So B squared plus C squared minus A squared. So it has to be that those two match up, divided by 2BC. Now our question is not in terms of A, B and C, so it's actually the point at T that we're trying to find. So just to update this formula to fit in our question, it would be cos T equals, and then the other sides are F and Y. It doesn't matter the order of these, because the order in which you add things or multiply them doesn't matter. So we've got an F and a Y, so we'll just do it in alphabetical order. So let's go F squared plus Y squared minus little t squared. So these need to match up. So these need to match up, divided by 2FY. Okay, and then we're just going to go ahead and populate that equation with the actual numbers. So little f here is the side opposite to big F, so it'll be this one. This is little t, and this is little y. So we've got little f first, so it's 5.6 squared. And even just populating the equation, you're well on your way, and you're starting to generate marks, plus y squared, which is 10.3 squared, minus the t squared, which is 7.2 squared. Okay, like this, and we're dividing that by 2 times 5.6 times 10.3. Okay, so once you've got to that point, we're just going to put this carefully into the calculator. You might want to break some of this calculation down. It's quite a lot to put in one go. If you're using a calculator that's got a fraction option and you can see the fraction on the display, then that might work okay. I'm using a phone calculator, which is not quite ideal. So I'm just going to break my calculation down. First of all, to work out the numerator, the top part of the fraction, and then I'm going to work out the denominator separately. But you can do it all in one go. If you're going to do it all in one go, just do it really carefully. So I'm just going to pull this down to here. So we're still cos t at this point, and that is equal to, so the top line here, the numerator, comes out to be 85.61. And then I'm just going to work out the denominator. And like I say, you can do this all in one go, but if you are going to do it all in one go, just be ultra careful. So I see a lot of students try to do this calculation in one go and they kind of get a little bit lost and the answer comes out a little bit muddled. So, okay, this looks a little bit weird, but remember that when we're trying to find an angle using sine or cosine, this should come out to be a decimal number. So we're looking for a 0 point something number, which this one will come out to be. So that looks good to me. because remember you still need to do the inverse at the end to get the actual angle. So this has come out to be 0.742117. So make sure you use quite a lot of decimal places here, and that would carry on actually like that. So the angle T itself is going to be cos inverse of that number, 0.742 blah blah blah. And this number will be stored on your calculator. So when you actually come to put this in the calculator, you can just use the A and S button. So just set that up as cos inverse and then your answer button. That answer will store that previous number so that you get the full number. You don't need to retype it. If you do retype it, make sure you use at least 4 or 5 decimal points, or it will throw the final answer off enough to lose a mark by not getting it correct. So that's come out to be 42.1 degrees. So looking at the diagram, that looks reasonable, doesn't it? That could be 42.1 degrees. So that tells us then that the bearing that we were looking for, so the bearing of y from t is going to be equal to 240 plus 42.1, which is 282.1 degrees. And that looks pretty good, doesn't it? Because it's spinning almost all the way around a full circle. So getting on for somewhere around 300 degrees looks to be reasonable. So that's the final answer, but not an easy question, that piecing together a few different things. Bearings questions tend to always be a little bit challenging, and just seeing those north lines can be a little bit off-putting, but remember ultimately they are just sine or cosine rule questions. In this question, we're being told that this is a straight line equation, and we're being asked to find the point where the line cuts over the y-axis, so in other words, the y-intercept. So clearly this is not in the correct format of a straight line. If it was in the correct format of a straight line, which remember is the y equals mx plus c, then we would just be able to read off this n number, the c value, which is the y-intercept. So for example, if we had the equation y equals 3x minus 7, then that minus 7 is the y-intercept. So to answer the question, we would say that the y-coordinate where the line cuts over the y-axis would be at 0, minus 7. So remember, we need the 0 as well, because we need the full coordinate, and any point on the y-axis has got an x-coordinate of 0. So that's one way to do this question. The other way to do it would just be to realise that if you're on the y-axis, then you do have an x-coordinate of 0, and then we can use that information. So let's actually do it both ways. Let's start by rearranging the equation. So we need to get the y on its own, like y needs to be the subject of the formula. So let's just start by moving things away from the y. So that's going to give us 20 minus 2x on the other side. And because in the straight line standard form, we put the x term first, I'm just going to spin those around to make it minus 2x plus 20. Then we need to divide by negative 5 because we need to get it all the way to y. And we're going to divide the two terms individually. Don't just put it all over minus 5 because these two terms need to be separated out. So we're going to have minus 2 over minus 5, x plus 20 over minus 5. And then we can just tidy that up a little. So the two negatives here would cancel to give us just 2 over 5x, so 2 over 5 is a gradient. We don't need that in this particular question. 20 divided by negative 5, well 20 divided by 5 would be 4, so this has to be negative 4. So what we've done there is we've taken the straight line, which is in this sort of jumbled up non-standard format, and we've rearranged it by changing the subject of the formula to this. So that would then tell us that the y-intercept has got a y-coordinate of negative 4, so the full coordinate then would be 0, negative 4. And that's the answer we're looking for. But the other way we can do it is just to realize, well, if you're a point on the y-axis, so if you've got an xy axis like this, and a straight line, doesn't matter where you draw your straight line, it could be here, it could be here, any point that's on the y-axis, regardless of where it is on the y-axis, has got an x-coordinate of 0. So that has definitely got an x-coordinate of 0, regardless of what the y-coordinate is, and so is that guy. So we can do this problem in a different way, by just going back to the original equation. This is actually far more efficient and just saying, well, if we're trying to find the y-intercept, we know that the x-coordinate is 0, so we're just going to let the x equal 0. So that's then going to give us 2 times 0, so 2 times 0 minus 5y equals 20. 2 times 0 is just 0, so that just eliminates to give us just minus 5y equals 20. Just solving this equation by dividing both sides by minus 5. 20 divided by minus 5 is minus 4. So we get the same answer either way. And again, just remember to present that as a full coordinate. So 2 different methods. This method might be preferable in some scenarios because this method only gives you the y-intercept. This method gives you the y-intercept and the gradient. And a lot of these questions will ask for the gradient as well. So it would depend on the question as to which method to use, but ideally you should really know both methods. And the question would go the other way as well. If we were trying to find this point, the x-intercept, we know that that point has got a y-coordinate of 0. So we would just put a 0 in for y and then solve that to get the x value. So 2 different options there for answering that question. In this question, we've been given these 2 algebraic fractions which are dividing, and we're asked to express them as a single fraction, so we're trying to combine them into one fraction somehow. If you're ever dividing by a fraction, whether it's algebraic or numerical, that's always a slightly awkward thing to do. So we always want to change that into multiplying instead of dividing. And the rule is if you can change it to a multiply, you just flip the second fraction. So this is just equivalent to the first fraction we're going to leave alone. So n over n squared minus 4, changing the divide to a multiply, but taking the reciprocal, or basically flipping the second fraction to get this. That's useful because if you're multiplying 2 fractions together, you just multiply the tops and the bottoms, the numerators and denominators. So it's going to be n times n minus 2. So it's going to be n times n minus 2 divided by these 2 multiplied together. So that's going to be 3 bracket n squared minus 4. So at that point we have achieved what the question asks us to do, which is to merge the 2 fractions into one. We've written it as a single fraction, but it's likely that it's going to simplify, and so always looking out for opportunities to simplify, and they'll tell you in the question. Anyway, to simplify. So we simplify algebraic fractions by factorizing them. The top line's already fully factorized. The bottom line is factorized with a common factor of 3, essentially, although we never manually factorized it, it just happened to end up coming out like this. But this is a difference of squares, so that difference of squares will factorize. So the top line is going to remain the same, n bracket n minus 2. Then we're keeping the 3 as a common factor on the bottom line. N squared minus 4 factorizes into 2 brackets because it's a difference of squares, so n minus 2 and then n plus 2, or the other way around, it could be plus or minus, doesn't matter. And by getting into that form, we can see we've got a common bracket, a common factor, top and bottom, of n minus 2, so we can divide top and bottom by n minus 2. Essentially that just means cancelling these out. They don't automatically cancel, it's just because we're dividing top and bottom by those terms, but effectively it means they're going to cancel, leaving us just an n on the top and leaving 3 bracket n plus 2 on the bottom. So that is the answer to that one. That is the fraction in its most simplified form. In this question, we've been given this diagram which represents a locker, and we're trying to test whether or not Chris's umbrella will fit into the locker. So he thinks it might fit in if he puts it from this front sort of lower corner up to this top rear corner. So basically on the diagonal, his umbrella is 85 centimeters. So we've basically got to test whether or not that length, to find whether that length, P to M, is 85 centimeters or less. That means that this is a Pythagoras question, a 3D Pythagoras question, and they're not easy to recognize, these questions, and they're not easy questions. But if you think about it, let me just quickly draw this on in red pen. We're trying to find this diagonal here, so from point P all the way down to point M, so that length there. We can construct a right angle triangle by considering the length down to there, and then to there, and that's not easy already because we're trying to draw a 3D shape onto a 2D surface, so it can be tricky to get this one set up in your mind. So let me just imagine taking that triangle and putting it over here, which will maybe clarify a little what it looks like. So this would be our point P up here, and then we've got our right angle down there, and then this over here would be point M, and then we're just connecting these, and this line here, this length here, which has gone a little bit curvy in my case. Let me just quickly fix that. It's that length there, P to M, that we're trying to determine. But if we're going to use Pythagoras for this, then remember that with Pythagoras, if you're trying to find a side length, you need the other two sides to be able to do that. So the Pythagoras part itself will be easy enough. It's getting the other information to then allow us to use Pythagoras, which might be challenging, although it's already challenging getting to that point. So we're told here that the height of the locker is 70. That corresponds to the line vertically up and down from P. So that means that this side here is also 70. And we're trying to find this side length here, which means that we really need this length to be able to do Pythagoras on this big triangle. So this length here that we're trying to find corresponds to that side there on the original diagram. So it might be very tempting to say, well, that side is 40, because we're told that this side and this side is 40, which would mean that this here would be 40 and that there would be 40. But actually, that means that we've now got a right angle triangle here. So going from here to here and here, and this would be a right angle in there. And we need to determine whether that length there is 40 or some other number using the other two lengths. So if we now take that triangle, and this is where these questions get a little messy, we've now got a second triangle, which is basically on the base of the shape, where this would be point M over here, and this is a right angle in here, and then this point doesn't have a letter. Let's just maybe call that A or something, just to help us get orientated. And we know that that length there is 40, but that length there is the same length, so that's also 40. And the same with this one, that's 40 because that's 40. So that's going to be 40. So what we need to do is to do Pythagoras on this triangle to get that side length, first of all, and then that will correspond to that side length there, and we can do Pythagoras again. So tough question, a lot going on here. So let's do this one first of all. So if we just set this up, classic Pythagoras, we're trying to find the long side. So this would be, so remember in Pythagoras, the generic equation is a squared plus b squared equals c squared, but the more important thing is it's the two short sides added together and squared, or squared and added together, I should say, like this. So this is going to be a calculator question. So we can go ahead and just basically put this in the calculator. So that one, these two are both going to be 1600. So we've got 1600 plus 1600 equals c squared. So that's going to be 3200 equals c squared. And then we're just going to go ahead and square root that and see what we get. Okay, so c then would be the square root of 3200, and that comes out, according to my calculator, to be 56.6 using one decimal place, and this is in centimetres. So if we look at our diagram, could that be 56.6? Well, that's 40, that's 40. This is the long side, it has to be bigger than 40. So 56.6 looks to be reasonable. So that is this side here we've just found. Remember, we're ultimately trying to find this length here, which is this side here, but we know that that side and that side are the same. So we can now transfer our 56.6 over to here. And now we're just going to do Pythagoras again on this question, on this triangle. So again, we're just plugging into the Pythagoras equation, a squared plus b squared equals c squared. We've got the two short sides, so I'm going to go 70 squared plus 56.6 squared equals c squared. Now we're told in the question that Chris's umbrella is 85 centimeters long, so we expect the answer to come out to be something close to 85, right? Or else it's not really much of a question. So that kind of gives you a guide that this should eventually come out to be some number fairly close to 85. So again, just putting this in the calculator carefully. Okay, so this left-hand side here comes to 8,103.56. So that's our c squared. So then c will be the square root of that number. So 8,103.56. So square root in that, and it comes out to be 90. So that's 90. Okay, so what does that tell us? Well, that tells us this side of the triangle is 90. So that tells us then that from P to M is 90. So we can say P to M equals 90 centimeters, and Chris's umbrella is 85 centimeters, so there is going to be enough space there to fit his umbrella. So, tricky question, right? You've got to use Pythagoras twice. It's in a 3D shape. They're not particularly common, but they're not uncommon either. They do come up from time to time, but certainly not a guaranteed question. They tend to come up maybe every 2 or 3 years, something like that on the final exam. So you just got to have worked a few of these to know how they kind of go, how they kind of flow, because once you've seen a few of them, they are fairly similar. They always involve using Pythagoras twice. In this question, we've been given this somewhat tricky looking diagram, and we're asked to find the shaded area, the shaded region, which is this area in here. And notice that this is a 5-mark question, and a little tip for you is that 5-mark questions at Nat 5 tend to involve 2 processes. You've got to do 2 streams of working and then bring them together. Classic examples would be like volume questions, where you might need to make 2 separate volumes using 2 formulas and then merge the answers together by adding them or subtracting. It's going to be the same here, and that is a hint for you in the question that you're going to have to do something twice basically to get 5 marks. And what we're going to do here is to find that shaded area, which is basically the area between the big triangle and the sector. We're just going to take one away from the other. So we're going to work up the area of the triangle, we're going to work up the area of the sector, and take the sector area away from the triangle area. So let's start with the triangle. So that's the triangle O to B to C. It's a non-right triangle, so we need to think, okay, is there any way we can make, or how do we make the area of a non-right triangle? So let me just put this here. So we're working on the area of the triangle, so the triangle area. Well, there's a formula on the formula sheet that says that the area of a non-right triangle is given by 1/2 AB sine C. But what that essentially tells you is that if you've got a triangle where you've got point C here and little a here and little b, which means this would be big B and this would be big A and this would be little c, then all you really need are 2 side lengths, A and B, with the angle in between. So 2 side lengths with the angle in between, doesn't matter what the actual letters are, that's all we're looking for. That just happens to be the way it's written on the formula sheet, assuming A, B and C. So if we, well, we do have an angle here and we do have the side lengths. So not on the diagram, but they are given in the question. So O to B, which is this side here, is 38. So talking about the triangle here, this would be 38. That's all the way from O to B, 38 centimeters. And then we're told that O to C, the other side, is 35. And because those 2 side lengths are on either side of the angle, we've basically met this criteria to use our formula. So we can just say that the area of our triangle is 1/2 times 35 and times 38, or either way around, so 38 times 35, times the sine of the angle in between, which is 75. And it's literally just a case then of putting that into the calculator. So always put numbers into your calculator carefully. It's easy to make little numerical mistakes. And when you're working out areas, it's not always easy to determine whether the answer makes sense. You've just got to make sure you do the working very carefully. So times 35. Okay, so according to my calculation, this comes out to be 642.3, and this question was in centimeters, so that's going to be centimeters squared. Okay, so that's the area of the triangle. Let's now work on the area of the sector. So again, back to thinking, right, how do I make sector area? Well, there's a formula for that, isn't there? It's not on the formula sheet, unfortunately, this one. So sector area is given by the angle divided by 360 times pi r squared. And if it was an arc length question, it would be angle over 360 times pi d. So just need to know that. The question tells us that the radius, so here to here, is 30. So we've got that. We've got the angle, which is 75. So we're putting our attention now onto O to A to D, working with the sector. So that's 75 over 360 times pi times the radius, which is 30 squared. So obviously the sector area is smaller than the triangle area. So the triangle area came out to be this number. So we expect this to be a slightly smaller number. So that'll give you an indication whether you've performed the calculation correctly or incorrectly. So yeah, just putting these into the calculator carefully again. Okay, so my one here comes out to be 589, and again, that's going to be centimeters squared. And that's what we expected, right, from the diagram. You can see the two areas are fairly similar. It's just a shaded area that's the difference between them. So these numbers should be fairly small. So that tells us then that our shaded area, and there is a lot of work in questions like this. You've just got to be patient and take your time. They're not the worst questions to get just partial credit for. So the shaded area, 642.3 minus 589. So you could maybe do something like that non-calculator, but hey, if it's a calculator question, you don't want to put yourself under pressure, so I'm going to put that in the calculator. So 642.3 minus 589, so it gives 53.3 as the final answer, and that is centimeters squared because it's an area. So yeah, in addition to the technical work required for that question, make sure that if you see 5-mark questions that you have it in your head that it's going to be quite a lot of work in. They generally are. And like I say, almost always 2 streams of work in which you then bring together at the end. So that's the answer for that problem. In this question, we've been given a diagram of 2 cartons, which I've expertly recreated here. And we're told the heights and we're told the volumes. And unusually for this type of question, which is a similar shapes question, we're being asked to show that they're not mathematically similar. Usually these questions tell you the shapes are mathematically similar, which means that there's a scale factor between them. And then you proceed to work out something on one of the shapes, like you might be given this height and asked to work out the other height. In this case, we've been given all the dimensions and we're asked to show they're not mathematically similar in the first part of the question. So what we're going to be doing here is using these to work out the linear scale factor, using these to work out the volume scale factor, and show that something breaks down there. Because the way that it should work is that the volume scale factor, which is just the scaled up factor you required to get from this to this number, should be equal to the linear scale factor, which is the scale factor you use to get between the length dimensions, cubed. So the linear scale factor equals, the volume scale factor is the linear scale factor cubed. The area scale factor, which is not relevant to this question, but does come up quite often in these, is equal to the linear scale factor squared. But this is really the formula that we want to violate in this question. We want it to not work out because they're not mathematically similar, the question is telling us. Okay, so let's just start by making the linear scale factor. So the linear scale factor just compares the lengths and will give you the sort of scale factor you need to get from one length to the other. So your linear scale factor depends on whether you're starting with a small shape going to the big, or to the big shape back to the small one. It doesn't matter which way you go, as long as you're kind of consistent in how you use that. So I think I'm going to go from the small shape up to the larger shape. There's a sort of informal formula you can use for the linear scale factor, which is the new dimension divided by the old. So new refers to the shape that we're going to, and the old is the one we're starting with. So in our case, we're going to start with the 16. That's going to be the old. The 24 is going to be the new. So this is going to be 24 divided by 16. So in this case, that would be what we would call an enlargement. But you can make your scale factor going the other way, which would be a reduction. If it's an enlargement, the scale factor should be some number bigger than 1. If it's a reduction, it should be smaller than 1. So this number here is 24 over 16. We could simplify that down just by dividing top and bottom by 8. So this becomes 3 over 2, or just, is that 3 over 2? Let me just check that. 3 over 2, yeah, or 1.5. So either using the fraction or the decimal version. I'll go for the decimal version. So all that's telling us is that that length there is 1.5 times that length. Okay, so that's our linear scale factor. What we're going to do now is work out the volume scale factor. And we need to be consistent here, right? Because we've gone from the small shape to the big one with our linear scale factor, we'll need to do the same with our volume scale factor. So we're going to take the similar sort of formula, so the new over the old, and the new is 576, is 1125 over 576, and we're just going to work out what we get for that. So 1125 divided by 576, and that comes out to be 1.6 1.95. So it should be that if these numbers are correct, then this, if the shapes are mathematically similar, then these numbers will make this formula correct. So let's just test that. So if we take 1.5, which is our linear scale factor, and cube it, what do we get? So 1.5 cubed is equal to 3.375. And that is not equal to 1.95. So in other words, that formula does not hold, so the shapes are not mathematically similar. Okay, so quite a tricky question, that one. There's various ways you could actually go about that. The other way you could do it is to take the 1.5, which is the linear scale factor, and make the volume scale factor, which would be 3.37. Let's just quickly have a look at it this way. This might be the way you've chosen to do it. So the volume scale factor would be 3.375. And that means that if they are mathematically similar, if you multiply that number by 3.375, you should get that number. So therefore, this would imply that 3.375 multiplied to 576 should equal that number there. But because we know they're not mathematically similar, then we expect it not to equal that number there. So this would be a second approach to this problem. That comes out to be 1944, which is not equal to 1125. So two different ways there to show that they're not mathematically similar. So in part B of the question, which I think we'll maybe do over here to get some space, they're telling us that the second carton has been redesigned so that they are mathematically similar, and that we're going to try and find the vertical height. And we're told that once they've become mathematically similar, that the volume of the second one is 1500. And this is a more classic similar shape question where you've got two comparable measures, both volumes, you've got one other measure and you're trying to find this one here. So we can do this one as an enlargement because we are going from the smaller dimension up to the larger, and we can use these two numbers to make our scale factor. Because these are the volumes, we're going to be making the volume scale factor. Because we're doing an enlargement, we're going this way. Remember, the formula is still going to be the new over the old. So the new dimension here is 1500 divided by the old, which is 576. So dividing those will give us our volume scale factor. So 1500 divided by 576. Okay, and that comes out to be 2.6. But remember, the volume scale factor just compares volumes, but we now want a scale factor to compare lengths. We want the linear scale factor. The linear scale factor cubed is the volume scale factor. The linear scale factor cubed is the volume scale factor, but it's the other way we're going here. So this would imply that the linear scale factor is equal to the cube root of the volume scale factor. So that's what makes this a tricky question. It's why it's the final question in the paper. So that means that our linear scale factor is going to be the cube root of 2.6, which is equal to, according to my calculator, 1.376, just to use a few decimal places there. So that then means that our height, or length, whatever you want to call it, let's just maybe call it height, is going to be equal to 16 times 1.376. Okay, and then just putting that in the calculator. And that comes out to be 22. 22 is fine actually, it's pretty much 22 dead on, so 22 centimeters. And if you look at the diagram, could that be 22? Could be. And does that make sense compared to like how it was before? Yeah, it's in the same ballpark, so these numbers could be sensible. If this came out to be like 58 or something, that's probably going to be too big in the context of the question. So difficult question that, is why it's the last question in the paper. First of all, having to do the not mathematically similar is very unusual. I've offered a couple of methods there. Quite a strange question that, highly unlikely to come up very often. And the more classic question is this one here, where we're just using the standard method to work out a missing side length or volume or whatever the question may be about. So those are the two solutions for that question.